Bismuth 209 is a heavy radioactive metal. It has a large nucleus with 83 protons and 126 neutrons. This nucleus is not perfectly spherical, it has a slight deformation making it look like a stretched or compressed sphere. This deformation is measured by the nuclear quadrupole moment. The nuclear spin of Bismuth 209 is 9/2. This means that the nucleus has an intrinsic angular momentum, like a spinning top. The quadrupole moment interacts with electric field gradients in the environment. This interaction can affect the energy levels of the nucleus. This makes the quadrupole moment an important property for understanding nuclear structure and interactions. The shell model is a simplified theoretical model. It is used to describe the arrangement of protons and neutrons within the nucleus. In the shell model, nucleons, protons and neutrons are arranged in energy levels or shells. Each nucleon has an intrinsic angular momentum, spin, and an orbital angular momentum. These angular momenta couple to give the total angular momentum of the nucleus. The quadrupole moment can be calculated using the single particle quadrupole moment formula. This formula is based on the assumption that the quadrupole moment arises primarily from the last unpaired nucleon in the nucleus. In the case of Bismuth 209, this is a neutron in the 1h9/2 orbital. The formula for the single particle quadrupole moment, Q_SP, is Q_Sp equals -3/5 times L plus 1 divided by J times J plus 1 times the mean square radius r squared. In this formula, L represents the orbital angular momentum of the unpaired nucleon. J represents the total angular momentum of the unpaired nucleon. And r squared is the mean square radius of the nucleus. The mean square radius, r squared, represents the average distance squared of the nucleons from the center of the nucleus. It can be estimated using the following formula: r squared equals 3/5 times r naught squared times a to the power of 2/3. Here, r naught is a constant equal to 1.2 femtometers. A is the mass number of the nucleus, which is the total number of protons and neutrons, 209 for Bismuth 209. Using the formula r squared equals 3/5 times 1.2 femtometers squared times 209 to the power of 2/3. R squared is approximately 30.6 femtometers squared. Plugging the values into the single particle quadrupole moment formula Q_Sp equals -3/5 times 5 times 5 plus 1 divided by 9/2 times 9/2 plus 1 times 30.6 femtometers squared. Q_Sp is approximately -22.0 femtometers squared. However, this calculated value represents the quadrupole moment contribution from a single nucleon in the outermost shell. To account for all nucleons in the partially filled subshell, we need to adjust the calculated value, Q equals 2, J minus 1 divided by 2J plus 2, times Q_Sp to Q equals 2 times 9/2 minus 1 divided by 2 times 9/2 plus 2, times -22.0 femtometers squared. Q is approximately -16.5 femtometers squared. The experimentally measured quadrupole moment of Bismuth 209 is about -0.37 femtometers squared. The discrepancy between the calculated and experimental values arises because the single particle shell model is a simplified representation of the complex nuclear structure. Factors contributing to this discrepancy include core polarization. The presence of the unpaired nucleon can distort the shape of the core nucleus, which is not accounted for in the single particle model. Configuration mixing. The actual nuclear wave function may involve contributions from multiple configurations, not just the single particle state considered. And meson exchange currents. Interactions between nucleons mediated by mesons can also affect the quadrupole moment, which is not included in the simple shell model. Despite the discrepancy, the calculation of the expected quadrupole moment is a useful exercise. It helps us understand the limitations of the single particle shell model. Studying these discrepancies provides valuable insights into the complex nature of nuclear structure and interactions beyond the simplified model.